When engineers design complex software, they begin with a serious challenge. They have to translate ambiguous, multi-part human rules into a rigid mathematical system, one that a machine can execute flawlessly without any need for interpretation. To achieve this, computer scientists rely on a foundational tool, the deterministic finite automaton, or DFA. A DFA is a strict theoretical model designed purely for pattern recognition and deciding whether a sequence of inputs is accepted or rejected. This handwritten breakdown shows exactly how every DFA is built on a strict 5-tuple mathematical framework. It is defined as a machine, M, consisting of a finite set of states, an alphabet of input symbols, a transition function that dictates movement, a distinct starting state, and a designated set of final accepting states. Let's apply this framework to a specific design problem. We need to engineer a machine that verifies a string of numbers against two overlapping constraints. The string must contain an even number of zeros, and it must end exactly with the sequence 0, 1. This state diagram maps the exact machine built to satisfy both conditions. By organizing a network of nodes and directional edges, we create a literal map of acceptable logic. Crucially, a DFA possesses zero memory and zero intelligence. Its entire capability is dictated purely by its predefined states and the deterministic rules mapping the transitions between them. To see how this static blueprint actively processes data, we can execute the machine by feeding it a test string, 0, 0, 1. Before any input is read, the machine rests at its starting condition. Here, that is state Q0. It reads the first input symbol, a 0. The transition function forces a movement along the designated edge, arriving at state Q1. Reading the next 0 triggers another transition, shifting the machine to state Q2. Finally, it reads the last symbol, a 1, and follows the transition path into state Q3. Because Q3 is a designated final state, indicated by the double-circled node, the machine terminates successfully. The string 001 satisfies the initial design constraints and is formally accepted. We can apply this identical logic to entirely different constraints. This new state diagram is engineered to ensure a string has at most a single occurrence of the pattern AB. Notice the linear progression away from the start state, leading toward a permanent dead end. If we feed this machine a test string like ABAA, it navigates this new topology step by step. The architecture is specifically designed to isolate and trap any sequence that violates the core rule. Looking at this transaction path, we can verify the exact sequence. The string routes through Q0, Q1, and terminates safely in Q2, an accepting state, without ever triggering the trap. A state machine's configuration, the specific placement of its loops and terminal states, functions as the structural boundary of the language it recognizes. We can build machines to accept specific languages, but to understand computation fully, we must mathematically prove the strict boundaries of those languages. Automata theory frequently tests a specific premise, that the clean star operator distributes over the union. This visually straightforward equation proposes a specific formal claim, that the clean closure of A union B is equal to the clean closure of A union the clean closure of B. To test this, we have to understand the power of the clean star. The clean star is an operator that takes a set of symbols and generates every possible arbitrary combination, repetition, and sequence length from those base symbols. Looking at these handwritten parameters, we can set up a formal counterexample. We define two perfectly minimal disjoint sets. Set A contains only A, and set B contains only B. In formal systems, unproven algebraic distribution leads to incorrect proofs. Establishing equality requires demonstrating that both operations generate identical string sets across all possible inputs. We evaluate the left side of the equation first. Because the union operation sits inside the parentheses, the sets A and B are combined into a single pool before the infinite expansion of the clean star applies. As this list shows, applying the star to that combined pool generates a universe of completely mixed strings, resulting in every possible cross-combination of A's and B's. Now we evaluate the right side of the equation. Here, the clean star applies to set A and set B independently, fully expanding each set before they are ever joined together by the union. This split screen reveals a strict limitation. the right side forces strings entirely from set A or set B, preventing cross-contamination. We isolate the mixed string AB, generated on the left. Mapping it to the right fails. It's mathematically impossible under strict isolation. The conclusion is absolute. Because a single valid string from the left cannot be generated by the right, the entire equation is strictly false. The clean star does not distribute over a union. Up to this point, DFAs have acted as passive gatekeepers, simply accepting or rejecting data. But practical computing requires machines that actively generate continuous output streams. To generate data, the standard 5-tuple expands into a 6-tuple definition. Looking at this list, the architecture now includes delta, representing a defined output alphabet, and lambda, which is the specific output function. This addition gives us our first major output architecture, the Moore machine. A Moore machine operates under one defining constraint. Its output is strictly bound to the state itself, completely independent of the input symbol that originally triggered the transition. You can see this visual syntax directly on a Moore diagram. The generated output values are physically embedded inside the state nodes. Mechanically, this means that simply arriving at a state automatically and unconditionally forces that specific output to trigger. Moore machines are highly stable and predictable because of this rigid state output binding. However, that same rigidity often requires a bloated, high state count architecture just to handle complex logical routines. To solve the bloat problem, engineers rely on an alternative output architecture, the Mealy machine. As detailed in this handwritten note, the core mechanical distinction of a Mealy machine is that the output function is no longer tied just to the state. It relies on the specific transition event, utilizing both the current state and the current input symbol. This completely changes the visual syntax of the diagram. The output values are stripped away from the nodes and attached directly to the directional transition arrows. This side-by-side comparison reveals a crucial timing shift. The Moore machine waits for a path to complete before outputting. The Mealy machine changes output instantaneously, mid-transition. By offloading logic to transitions, Mealy machines achieve massive efficiency, producing identical results with significantly fewer states. This reduction in states and increase in speed comes with an engineering trade-off. Compressing the machine requires highly complex, dense transition mapping that is inherently harder to debug. Advancing from basic DFAs to high-efficiency Mealy machines demonstrates that computational design is always a continuous process of strictly matching specific mathematical tools to the technical constraints of the environment.